Okay, that's good. Thank you. Appreciate that. Do I need to start my video? I don't know. Okay, now hopefully they can hear me. Sorry about that, guys. So if we look at this one, right? So we're looking down this atom, right? So if we're looking down that atom, what do you see? And the circle represents that carbon that's in the middle. Well, what's attached to that carbon? Well, if I think about it, I have a line going down, right? So if I'm looking here, right, I have a line that's going down. Okay, that line has a CH3 attached to it, right? Then if I'm looking here, right, then off to my right, right, what's coming out of the page off of my right here is a hydrogen. And then here, if I look at my hydrogen there, I see the other hydrogen going this way, right? So that's that first carbon, and this is called a Newman projection. Now, this back carbon, if this big circle represents that front carbon, do I actually see this back carbon? Not if I'm looking right down that bond, right? The first carbon is hiding the second one, but I should see what is attached to it, right? So what's attached to that back carbon is a CH3 that's going where? Up or down? Down, right? Now, if I show it exactly where it is, I won't see it, right? Because it's hiding behind that CH3, but I'm going to skew it a little bit, right? So I'm going to take the angle and I'm just going to change my perspective and I'll draw it right here, right? Kind of showing that it's close to it. And if I look at my hydrogens, again, we have one coming out to the right, one coming out to the left, both on the top, right? I have a hydrogen here, I have my hydrogen there. If we think about the fact that this methyl group at the bottom is behind the other methyl group, right? So we have two methyl groups. If this was the moon and the sun, what would we call this? Eclipsed. And that's what we call it here, eclipsed. So this conformation is called eclipsed. And again, a conformation is just how we draw something in space, right? It doesn't change the atom, it's how the atom is sitting in space. If we were thinking about proteins, it'd be how the protein is folded in space, right? The conformations that a protein takes in all of its carbon atoms determines its folding pattern, and its folding pattern determines how it interacts, right? So if you can get certain folding patterns, it can actually turn on or turn off genetic activities, right? Whether you have brothers and sisters, you both may have very similar genetic code, but depending on, I don't know, environmental reasons, whether your mother ate pickles, whether your dad ate a steak, I don't know, all kind of things, right? It changes the conformation. So this is where this is coming from. Okay, so that's the first one. This is an eclipsed. If we think about an eclipsed, right, what's happening between these CH3s? Well, let's go up here and let's draw in, and I'm gonna purposefully draw the hydrogens pointing towards each other. What is happening between these two hydrogens? They're going to be bumping into each other, right? They're going to be too close to each other. And so this is going to cause strain. If we look at the second one, let's draw it again in a Newman projection. We start with a circle. And the same thing, what's going down is my CH3. What's coming to the front, my right, is the H. Let me erase this. Doesn't have to be wedge, just okay. But then when I look at the back carbon, right, my eye is here and I'm looking at the back carbon, where's the methyl group? based on my perspective and based on this methyl group, that methyl group is behind it or straight across from it. See, it's going to be straight up, right? So that gives us CH3. And then when we look at our hydrogens, right, again, we have left and right, but now they're going down, right, instead of up. So when I redraw that, when I put that in the Newman projection, I get this. So this form is called staggered. And because all of the group, all the atoms, right, are staggered to each other. So if we, again, we draw in our hydrogens on those two methyls, my hydrogens are now, you don't have that interaction, right? This hydrogen is actually pointing in the middle of that one. This hydrogen is pointing in there. We have lots of space, right? So there's plenty of space for those methyl groups. Because of that, the staggered is going to be lower energy, right? It's going to be the more stable form. Eclipse take energy, right? We're getting too close, but then staggareds, right, provide space, and therefore we don't have to worry about the repulsion. And again, the repulsion of this comes from the fact that every single atom has electrons on the outside, right? So they're not attracted to each other, they're repulsing because they're all negative on the outside. Okay. So this is the basic conformations of an acyclic. Now, when we go through these, let's start again with our most stable. Okay. We can rotate these. It's habit. I always want to draw it up because that's where it should be. So if we think about this, and I should have brought my little model with me, I'm going to be rotating those two atoms, right? And as those atoms rotate, I'm going to be going through a series of conformations. So the first one, we start here, and I'm going to draw the Newman projections. Okay, this is the first one I've shown up here, so we'll call that the starting point 0. And then if we shift, actually there's more. We're not going to moving the front carbon, so we're going to leave that as the CH3, H. But now I've got this CH3 that is going to be eclipsed with that hydrogen. So if we look here, there's a hydrogen, and these two are going to be eclipsing each other. So not a methyl eclipsing a methyl, but a hydrogen and a methyl eclipsing. Okay, if we rotate that again, oh, that's weird. Didn't know the program did that. If we rotate again, then we're going to end up, again, we're not changing the front carbon, so we're just changing the back. I end up with another staggered. All right, so here's staggered, eclipsed, staggered. Everybody following? So we're just rotating that back carbon 60 degrees each time. Then our next one is going to be This one, that was the first eclipse we showed. First one doesn't change, and now the back one is eclipsed. We do another 60 degrees. And then another 60 degrees. And so first carbon stays the same. Oops, stays the same. And then now we've got the CH3 going to the other side. Okay, front carbon doesn't change. Okay. And then if we label these, this first one is what? Eclipsed or staggered? Eclipsed. Second one, that's going to be staggered. And then the third one is going to be eclipsed. Okay. Yes. This one and that one. This one. This is coming out, right? Yeah, sorry. This one is coming out at you, so therefore it's still not in the plane. So that puts it here. So if you look at it, we go through staggered, right? Eclipse, staggered, eclipse, staggered, eclipse. So we're just rotating. And then this one, right? After this, I go back and I start over again, right? So this is energy of rotation. So if we have single bonds, we have an energy of rotation. And that energy of rotation is going to be the energy it takes to go past the highest energy eclipse form, right? And which of these eclipse forms is going to be the highest energy? The one where I have a methyl group overlapping a hydrogen, right? A methyl group overlapping a methyl group, or a methyl group overlapping a hydrogen? Which would cost you more energy to go past that barrier? Well, the methyl groups, right? Because they're actually going to have the hydrogens pointing at each other at some point, right? And methyl groups can rotate too. So you got to think about that. But if I have a hydrogen, right? Here's the hydrogen, here's the methyl. There's more space between those. So it's a lower energy. So we can draw an energy diagram for this rotation. And if we think about our staggered, same thing happens with our staggered, right? Is this staggered going to be the same energy as this staggered and that staggered? Well, this staggered, the methyl group is between two hydrogens, right? But over here, I've got the methyl groups next to each other. They're not eclipsed, they're not that close. You know, they're not like this, but they're like that, right? And so there's still going to be a little bit of interaction. And so this is going to be higher energy than this one. So we can start with this lowest energy one, and then we come up to a staggered, eclipsed, but it's an eclipsed with a methyl and a hydrogen overlapping. And then I come to a staggered, but now the staggered has two methyls in close proximity, not opposite each other, but close proximity. So it's not going to be as low a energy as the first one. So I can, pick an energy there. And then from there, I go to this eclipse, which is going to be the highest energy because I have two methyls that are overlapping. So when I draw my energy diagram, oh, what's wrong? Okay, then I'm going to go to a higher energy state. And then when I come back down, I go to a different staggered, right, with the methyls near each other. So it's a different chiral representation. You can think about these two as actually being mirrors of each other. So they're going to have the same energy, but they're not the same. So then go back down here, and then we end up with the eclipse with a hydrogen overlapping. So if we look at this, and again, it'd be nice if it was perfect, but it's not quite, right? These are my energy levels. And this is the rotation energy. Well, it's actually the stability, but it gives you the rotation energy. Now, because we have different forms here, we have some different names. So the staggareds, they are all staggered, but you have anti and gauche or gauche antis. So the lowest one is anti. That makes sense because the two methyls are anti to each other. And then when you go to the third one over here, right, they're not overlapping, but they're next to each other. That's when we use the term gauche or gauche. And this one would also be known as gauche. Now the eclipsed, you don't see eclipsed energies, right? They're the higher energy. So you don't see those as much. So therefore they don't have special names. But I usually call them the low energy. And it's not the lowest energy, but it's lower, I guess I say lower energy eclipsed. Right? And the higher energy eclipsed. Right? Questions about conformations or acyclic conformations. Now, you always have eclipsed and staggered, right? But you may not have anti and gauche. An example of that would be, ethane or ethanol, right? So if we look at ethanol, and to make it a little easier, right, we're looking at this side. And at this form, what's on the back? Well, it's the hydrogens, right? So I have these hydrogens. And then if I rotate it, I'll get an eclipse form. If I rotate it, I'll go back to a staggered form. And if I rotate it, I'll go to an eclipse form. And you should be noticing that the eclipsed are all the same and the staggered are all the same. And that's because what I have on the back carbon is all identical. Right? They're all 3 hydrogens. So if we go through all of those rotations, and it gets a little confusing because all the ones on the back are hydrogens, right? Right. All I have here is staggered and eclipsed. And if I try to draw the energy diagram here, I would just have 2 levels. Okay, so when you're drawing Newman projections, you notice what I do. I draw the eye, right? You should do that when you start out, right? And you should think about what's attached to your front carbon. Also notice every time I draw a Newman projection, I only rotate what? The back carbon. If you don't keep one of them static, right? And you could keep the back carbon static if you want it, but you got to keep one static. If not, then you're rotating both of those and it gets really confusing really fast. Also notice that you may only have 2 conformations, right? But your maximum number is going to be 6. Newman projections are also always drawing down a bond, right? So it's drawn down this bond. So if I have a large molecule, okay, and let's say we were trying to draw the Newman projection of this, I would need to give you some information, right? So I would want the Newman projection down the C2C3 bond. So again, think about it. So this is carbon 1, 2, 3, 4, 5. If there was something else attached to that, right, it might be different. So name your molecule and see what carbon is first. If I'm going down the C2C3, that means that I'm looking down this way. Okay, and notice it says C2C3, not C3C2, right? So it's going this direction, not the opposite direction. And then when I draw that, and if it said most stable form, the zigzag is the most stable form, right? So that's a CH3, hydrogen, hydrogen, right? You can draw them in if it helps you, especially as you're getting used to this. And then on the back, we have 2 hydrogens, right? So we have our hydrogens, hydrogens. But then what is attached to the C3? So if we look at what's attached to the C3, it's this group. Right? And you can draw it CH2, CH3. Sometimes it's helpful if you just go ahead and draw this so you'll know what's attached, what is included, which is just the 2 carbons, and what's not included. Okay, so on the online homework and the exam next week, you'll be expected to convert things, right, to their conformation drawn in a perspective drawing to its Newman projection. Okay, you should be able to do energy diagrams, understand those. You should be able to label staggered and eclipsed. You should be able to label anti and gauche, right? So up here, this is anti, right? This is gauche. And this is gauche. Okay. Questions about acyclic conformation? Yes, ma'am. These 2 here, these 2, they're right here. The CH3 is here. This CH3, well, the way it's drawn, you're only looking down one bond. You're not looking down all of it, right? So if you really wanted like what it looked like, then this carbon here would be down and behind that carbon, right? But that's not the way Newman projections. It's just what is attached to those 2 carbons. So therefore, you can abbreviate that as just CH2, CH3, right? If you wanted to show all of it in space, kind of one of those stick and ball models, if you use the stick and ball model and you had looked down that bond, then the CH3 would have actually disappeared behind that. Okay, but it's not disappeared here, it's disappeared there, right? You're a long distance away, so it doesn't cause a problem. But in a Newman projection, we can do whatever's attached to this, right? We just have to represent that. We don't have to show the perspective or the Newman projection of that. So you're not extending the Newman projection out. Okay. Other questions about these? Okay. Okay, so this is acyclic conformations, right? And of course, this does build into SNR that we went over last week. This is kind of the step up to that. Now, the next thing we need to look at is cyclic. Now, if we look at cyclics, right, let's dissect these, right? Let's start with the cyclopropane, and cyclopropane exists. Now you may say, why do you say exists? Well, think about it. Let's look at this carbon right here. It's sp3, right? What is sp? What is the hybridization? It's sp3 because it has 2 hydrogens, right? So it has 4 groups. So sp3. What's the bond angle for an sp3? What does it want to be? 109.5. What is the internal bond angle for a triangle? 60 degrees, right? So internal equilateral triangle, 60 degrees. What does the carbon want to be? 109.5, right? So the difference between these two is ring strain. Let me spell that better. So it exists. What it means is it's having to push what wants to be a 109.5 degree angle to a 60 degree angle, right? Of course, that also modifies the hydrogen angles, right? So it's having to squeeze into that. That means that cyclopropane, if I burn cyclopropane, if it combusted, it would give more energy than just acyclic cyclopropane. There is an energy difference between those that comes from this ring strain. There's more energy bound up in that cyclopropane, okay? So that causes this ring strain. Now, the molecule wants to relieve that ring strain, right? So there's some ring strain there. Can I relieve the ring strain in a 3-carbon group? If we think about 3 carbons, is there any way I can take a 3-carbon group and do anything to relieve that strain? No, it's 3 carbons, right? Can't do anything. When we look at 4 carbons, again, we have, no double bonds. It's going to have 4. So this is an sp3 that wants to be 109.5 degrees, right? But this is a 4, right? It's a cube. So this is going to be 90 degrees. So we have ring strain between that 90 and that 109.5. And again, it's just 4 carbons. So if we think 4 carbons, what we can do with 4 carbons, we can't do anything with the 4 carbons, right? They're all in the same plane. I can't do much. Okay, so it's planar, meaning that's all in the same plane. Planar, it's all in the same plane. I'm not going to be able to relieve that strain. It just has a lot of strain in it. For those of you online, you did not realize that the timer went out on the projector, and now I'm waiting for the projector to turn off so I can turn it back on. Okay, so this ring strain is something that's inherent in cyclics, right? In the cyclic, right, there is some energy that is saved. What kind of energy would be saved in a cyclic that would overcome some of this ring strain? Well, if we think about it, if we have an acyclic molecule, a non-cyclic, right, it's always wiggling around and there's always a lot of entropy energy. That energy is not there when it's in a cyclic. Now, a 3-carbon group, it does take that there's some extreme reactions you have to do to form it, but cyclopropanes are even exist in biological molecules. Right? Butanes are a little rarer. I mean, so 4-carbon groups are a little rarer, but they also aren't so rare that you don't see them, and they're not overly difficult to make. So When we go to 5 carbon groups, and now we really have to go back to our geometry and think about pentagons, right? We have sp3, that's going to be 109.5. And now what's the internal angle of a pentagon? Okay, so it wants to be 105, right? So we're not that different here, right? But now when we start looking at 5 carbons, if I can, I don't know how to do 5 carbons. If we do 5 carbons, right, now we have some flexibility. So 105 if it was planar. And so what we start to see with cyclopentanes is we start to see a conformation. It's a little hard to show there. What they call it is the envelope. And I don't know if you've ever seen an envelope. It used to be common at my age. You had an envelope. You'd have the little lid here, right? And the envelope always, this part always came out at you, right? So if we think about it, this is coming out of the plane a little bit. So 4 carbons are more or less in the plane, and then 1 is kind of coming out. What this does is it modifies from the planar angle to an internal angle of 109.5. Draw that a little bigger. So this angle now is 109.5, which matches the sp3. Now in a 5-membered ring, it's still straining to do that, right? And the reason it's straining to do that is if you show the Newman projection, your Newman projection is going to have some near eclipsed groups, right? So if we think about even a 3-membered ring, right? Since these hydrogens here and these hydrogens here have to be aligned, they're eclipsed, right? These hydrogens here, these are all eclipsed. If we think about this carbon and that carbon, they're eclipsed. They're also cyclic. But when we get down here, we're starting to get 109.5, but we still have some near eclipsed hydrogens. We don't have staggered hydrogens, right? So we're not getting enough bending in that ring to get both 109.5 degree angle and now fully staggered hydrogens. When we go to a 6-membered ring, well, that's an ugly 6-membered ring. Here again, we have an sp3. But now if that was planar, what would be the internal side of a, so 120 degrees, right? So what happens here is the conformation is this. So it forms a chair conformation. That allows all of the internal angles to be 109.5. It also allows the hydrogens to be eclipsed. I mean, to be staggered. So let's draw this again. And I'm gonna put my hydrogens in. Okay, so that set of hydrogens, if you notice, this hydrogen here and that hydrogen there are anti to each other, right? One is going above and one's going below. Again, same thing here. If we look at this one and that one, again, we see them. And let me put this a little bit darker. Sometimes when you draw these, they kind of look like optical illusions because the front and the back start to invert. So if you draw the front one, what you want to be front a little darker, then it'll help. And then here again, we see this hydrogen and these hydrogens, right, are anti to each other. So they're all anti. So we've drawn a conformation where we have all of the hydrogens anti to each other, right? These hydrogens, these are the easiest ones to look at. And if they're anti, right, that's the most, if this had been a set acyclic, that's the most stable conformation. So here we have 109.5 degrees and we have an anti-arrangement of all of our hydrogens. So we have no near eclipse, we have no, we have the perfect anti, not even a gauche, we have an anti. Okay, if we look at the other atoms, and I'll change colors here, let's use red. It's a little harder to see that they are in the staggered, the anti-staggered conformation for this group, but they are. Okay. Now, there is a difference in stability between these two sets of hydrogens. If we look at the blue set of hydrogens, we can see that we have a little bit of interaction between those. Do we have the same interaction between the hydrogens that are red? No, right? Because if you think about it, these two are up here, right? So they're both above the plane. Now they're not 1 carbon 2, they're 1 3, right? So they're on the first and third carbon. So 1 3 interactions. But these are closer together, right, than those, right? So the ones that are in red on my drawing, right, they're actually out away from the ring, where the ones that are blue are above and below, right? So there's going to be interactions above and below at a 1 3 spacing. The ones in blue we call axial. The ones in red we call equatorial. And the equatorial is going to be more stable than the axial. They're going to be more stable because they have more space. Okay, before we get into the next step, what we do is a little bit of a tutorial on drawing these. Okay, so they're not easy to draw. In the books, the textbooks, and on the online homework, you'll see that they don't look exactly like mine. They're a little bit skewed. I'd say they're more accurate, but it's also really difficult to draw. So what I'll go through now is kind of a drawing of how to get the structure I have. So start with 2 lines that are parallel but not totally lined up. And then starting at the short side, we're going to draw a peak going up. So wherever that is, the peak going up. Starting from the short side, we draw it towards itself, and oh, that was ugly. And then we can draw our hydrogens, and I'm going to start with the axial hydrogens, and I tend to just draw those straight up. It makes it clear in my mind while I'm working in the problems, and when I see a computer drawn one, it's not that off, right? It's easy to identify. Again, this is not 100% accurate, but it is really easy to draw this way, right? And it'll help because what tends to happen is I see all kinds of things. Let's see, one of them, the ones I see is something that looks, well, that's not what I wanted. Something that kind of looks like a twisted, like that, you know. And if you look at the ones in the books, it kind of looks like that. But if you're not really careful, you start to get things that kind of don't work, right? And when you start to put your hydrogens in, I don't know if those hydrogens are equatorial or axial, right? So if you're trying to answer one of these, it's better to be a little bit inaccurate in your angles and clearly express what you're trying to say than it is to draw something funky where I'm trying to guess what's going on, okay? So that's the first ones. Let's put in our equatorial. Now the equatorial is a little bit tricky. The axial, you just draw them straight up. It's clear then, right? The axials, the ones on the end, draw those out, and it's okay if they're not perfectly level because you do want to kind of represent that 109.5. But then when we're looking at, let's say, this carbon right here, what I want is for the hydrogen to come out kind of in this direction. And the way to make it line up right so that I'm not getting confused on my hydrogens, like my example up here, is I want to use that as my guide. So I'm going to draw this parallel, right, with that. Then when I draw this, the hydrogens on here, I'm going to use this as my guide. And I'm going to try and use, so again, I'm drawing this parallel, as close to parallel as that as I can. Here again, I'm going to use that back carbon bond. So this one matches that one. And then for here, I'm going to use this one. And again, it's always acceptable. Give yourself a little bit of shading so you know what's coming forward and what's going back. Okay, so I don't know if any of you have ever seen those like ratchet lawn chairs where you can kind of flip them around, right? And they usually have a head because it's got the white part on it. But they used to be really common when I was a kid. And we used to play with them and we get stuck in them and get your sister's hair stuck in the little grinding things, and you'd be in trouble and you wouldn't get to sit on them anymore. But they would fold up like this so you could put them away, right? But you could have them like this, right? You could have it like that, or you could flip it over and have it like this, right? So you could put the head down and the head up, right? They would go either way, right? That flip flop, right, is what happens with this. If you think about this, this is not going to be a static molecule. These are all going to be rotating, right? Even if we think about our conformations for acyclics, it's going to be rotating. And if there's enough energy, it'll rotate past an eclipse to get to another stagger, right? What happens here is that I also am going to have conformational flipping. Now here I can't fully rotate, but I can flip. And so what's going to happen is that I'm going to flip this coming down and that going up. So to show the flip, I'm going to, again, draw two lines, but now I'm going to shift them the other direction. It's important to know that I'm flipping and not rotating. Okay, when you see them in the book, you're going to sometimes look at a flip and it'll look like they just rotated into space like this. Okay, that's not what's happening here. I'm taking this side that was down and this side that was up, and I'm flipping them this way, right? I'm rotating around those two bonds. Everybody do this with me because you'll feel the rotation. Okay, put your arms out like this, right? If you're on at home, do this too. Your roommate will look at you funny. Okay, so just flip them over. Do you feel your arms and your shoulder sockets rotating? That's what's happening with the carbon atoms, right? So these carbon atoms are actually, the bonds between those are rotating. So now I'm going to go in and notice my color change. These are the red hydrogens from the beginning. But now what was equatorial, right, is now axial. So the red equatorial hydrogens now have flipped into an axial position. The blue axial hydrogens are now flipping, and again, take your time, kind of draw those parallel the best you can. So my blue were axial over here, right? And now my blue is equatorial. And remember that equatorial have more space. So what's happening in a normal cyclohexane like this is going to be flipping back and forth, right? It's going to be flipping back and forth. And it doesn't flip like this, right? Okay, so it never goes through this position. Okay. This position is called boat. In the boat position, every single atom is eclipsing another atom, right? So that's the highest possible energy. What happens is to go from one chair to another chair, both sides are doing it at the same time, and I can't show it with my arms, but where you're going is going through a twist boat, right? It's a modified form. Think about everything rotating at the same time. You're not doing one side and then the other, right? You're not doing this, right? That goes through the boat, and that's the highest energy. Okay, but these are always going to be going back and forth, back and forth, back and forth. So your equatorials are going to be flipping to your axials are going to be flipping to your equatorials. And so your hydrogens, really the energy around your hydrogen is stabilized. They're all going to be equivalent, okay? And there's some good videos online if you want to see the twist boat and the kind of rotation. So now let's take and look at this molecule. So we draw our chair, and now I have a methyl group on here. And the question is, do I put the methyl group axial or equatorial? Well, where would the methyl group be most stable? Would it be most stable in the axial position, or would it be most stable in the equatorial position? The equatorial is going to give me more space for that methyl group, right? So its interactions with the hydrogens that are staggered, but the hydrogens that are next to it are going to be lower if it is in the equatorial position, right? So they're this versus that, right? So they're kind of waved out away from the ring versus being straight and above the ring. So we can draw that, right? Now, if we flip this, that's going to flip to the axial position. Which of these is going to be more stable? Well, the equatorial, because it has more space, right? So we have less interactions. But whenever we go to the axial position, why is this less stable? Well, it has to do with the interactions, the 1,3 axial interactions. So it's sticking above the ring and it's going to be closer to that 1,3, not the 1,2, like as in eclipsed and staggered, but the 1,3. So that's what we're watching for in the cyclohexane chair conformation. So if I ask you to draw the most stable mono-substituted cyclohexane, you're going to put the substituent, the methyl in this case, in the equatorial position, right? That makes sense. It does not have the 1,3 actual positions. If I say what's the highest energy conformation, you'll draw it in the axial. Okay. The big question comes, what happens if you have more than two things? If you have one thing attached, put it in the equatorial, you're safe. What happens if I have two things attached? And for two things attached, notice I'm now needing to designate whether those are up and down, right? Because this molecule and this molecule are not equivalent. And that's because if you think about it, this does have a plane of symmetry here, right? So it's not chirality, but it is a stereocenter. Because if we look at, if this was a plane, right? Here we've got both CH3s above the plane. But over here, if we had a plane, right, we've got one CH3 above that plane, and we have one below the plane. Okay, and if they're on opposite sides, what do we use for stereocenters if it's on opposite sides? It's going to be trans, right? So you'll see this could be called, if I was writing this out and didn't use the R, there's no R and S, right? But this does have a stereocenter, so I would say trans dimethyl cyclohexane, right? Trans 1,4 dimethylhexane. If they're on the same side, I use cis. So this would be the cis 1,4 trans 1,4 dimethyl cyclohexane. So let's draw the chair forms of these two, the trans and the cis. Again, start by drawing a chair and then put one of your groups, and we'll put this one here, we'll call that A. So here's A. And now my CH3, I put it up, right? The other CH3, is it on the same side or the opposite side of the CH3, the first CH3? Okay, it's going to be opposite, so I can draw it this way. And if you can think about it, it was like this, and I've turned my hand, and now I'm facing it this way, right? So I'm taking my hand, and now I'm doing the hello sign to now I'm just kind of going flat, right? And so that's what's happened here. Okay, if we draw the other one, again, let's start and let's try and use the same. Now when we put our CH3 up, I can use a diagonal line between those two to help. Now, if we think about it, we have this position and that position. Which one is going to represent that these are on the same side? The axial position going down or the equatorial position? If we look at that blue dotted line there, right, it's going to be the equatorial position. So the cis has both of those CH3s on the same side. Okay, so one more step, let's flip it. So the methyl that was here at the 1 position that was axial is now going to go to the equatorial. The one that was at the 4th position that was axial is going to go to the equatorial. And actually, it should be. Okay. And then on the other side, the methyl that was up here that was axial, is now going to flip to the equatorial position. Axial flips to equatorial, equatorial flips to axial. And then over here, this one that was equatorial is going to be now in the axial position. Okay, so let's label these as far as where their substituents are. If the first one we see, we have an axial, right? They're both in the axial position. When we flip it, now they're both in the equatorial position. Which of these 2 conformations is going to be the most stable? The equatorial, right? That's the most stable. Okay, in the second one, we have an axial equatorial, right? And we have an axial equatorial, or equatorial axial, if you like. So in this case, is there any energy difference between these 2? No. Why? They're both methyl groups, right? If they weren't both methyl groups, would there be a difference? Yes. Which one would you want to be equatorial? The smaller group or the bigger group? The bigger group should be equatorial. It has more space. And remember, the reason that the equatorial is more stable is because of the 1,3 diaxial through space interaction, right? So space is important. And what type of space? Space close to the 1,3 axial or the space far away from the 1,3 axial? Close. So something that's branched closer in is going to need more space than something's branched way out, right? So you'll see a few examples of that when you look at some of the homework problems. Okay, so let's try a few of these. I'll draw the structure. You tell me what the most stable conformation is. Okay, so let's take a little time, draw those 2 conformations. And I'm losing battery really quick, so I'm going to go ahead and answer these 2 and talk through them. because if I let it die before the video starts recording, then we won't have video recording. So won't truncate much, but I'm down to 7% and just lost 3% in the last minute. So let's go ahead and look at these. So first, what you do is just don't worry about where everything is yet. Just draw you a chair, right? And then what I tend to do is take the largest group and put it first, equatorial, right? So if we look here, I'm going to put this one and I'm going to put it, let's see. Let's go ahead and put it here in, no, that's not going to work. So let's put the biggest group here, right? And then if we go around, we'll look at this position, right? And we have two positions there. We have the methyl. We could put the methyl here or there. Again, it is helpful to think about drawing a dotted line between those two to try and figure out which one's on the same side. And here, do I want them on the same side or opposite? I'm going to want it on the opposite side, right? So the CH3 goes here. I'm going to go ahead and show the hydrogen there just for this part. But the way I've drawn this, right, I've put my isopropyl in the axial position. Is that going to be the most stable form? No. So therefore, I can redraw that, flip it, put my isopropyl in the equatorial form, right? Now my methyl was equatorial, so now it's going to be axial. And so I end up with equatorial axial. So my isopropyl is in the most stable position. My methyl in this structure, right, this conformation, the conformer is going to be an equatorial axial. If I wanted equatorial, what would have to be the position of the methyl to the isopropyl? They couldn't be cis, couldn't be trans, they would have to be cis, right? So this is a trans arrangement in a 1,3, right? 1,3 trans gave me a equatorial axial structure. And this is the most stable. Questions about that? In the second one, again, just draw your chair. And we can put our methyl here, and we can put our ethyl. Now we need to put them on the same side. I find that if you go ahead and draw all your groups in, it helps you figure out what's on the same side and what's not, right? So if we're looking at this, which of these two down here are on the same side? This one or that one? This or that? This, that. Okay, that's going to be on the same side as the methyl, right? If we think about it, these two, right, are going to be towards the top of that ring. These two, right, are going to be towards the bottom. So therefore, I'll draw my CH2, CH3 here. But again, it's not a problem because you can just flip it. This is axial and this is equatorial. That's not the most stable conformation. So therefore, I'm going to redraw that. I'm going to flip this. Now my methyl becomes axial, and my ethyl becomes equatorial. So 1,3 cis, 1,2 cis is going to be equatorial axial. What would be 1,2 trans? 1,2 trans would be I'd be able to have equatorial. How about 1,3 cis? 1,3 cis would allow me to have equatorial, equatorial, right? So not all of the stereo arrangements have the same potential stability, right? A 1,3 trans is less stable than a 1,3 cis. And you'll also see that, and it turns out in biological systems as well, you'll see arrangements of these 6-member rings based on that, okay? Questions about conformations? Okay, I'm down to 2%, so I'm gonna stop this so we can make sure that we can record this for anybody that didn't